Hello everyone, welcome to the 8th lecture on the course Mathematical Modeling and Simulation. The objective of this lecture is to explain you the characteristic and the difference between the exponential and logistic growth and to give you some realistic examples of the logistic growth. So let's begin. As you have seen in the previous lecture, we have discussed a model of the population growth in which the growth rate is proportional to the size of the population. In the resulting model, the population was growing exponentially. But in the real world, we know that we have limited resources and exponential growth cannot continue indefinitely. Charles Darwin was first to recognize this fact, and in his description he wrote the struggle for existence, which states that the individuals will compete for the limited resources and the successful one will likely to survive and pass the traits that made them successful to the next generation at the greater rate. So this means that the exponential is not very much realistic. So what did ecologists do? They developed a logistic differential equation. We can say that exponential growth occur when the individuals are very few and there are plentiful of resources, and this model assumes that the relative growth rate decreases when P approaches the carrying capacity. Now what is this carrying capacity? Carrying capacity means the maximum number of population size that an environment can sustain. So they said that this relative growth rate decreases when the population size reaches this carrying capacity. That means when the relative growth rate reaches the size which an environment can sustain, then they take a constant growth and they cannot grow beyond that because of limited resources and competition among themselves and other species. So in logistic growth, we can see the per capita rate of increase declines as the carrying capacity is approached, as I have told you, and we can construct a logistic model by starting with the exponential model, and then we can add an expression that reduces the per capita rate of increase as P increases. So we can see like this, that this is nothing. If we cut this, this is an exponential growth, and if we multiply this with the term which reduces as per capita rate of P increases, then we can have a logistic growth model. Here P is a population size, and you can see that as the population size increases, this equation becomes smaller and smaller. This shows that the population growth rate also becomes slow. Now there is another way of deriving this logistic model. Let us see and go step by step to derive this logistic model. In the previous lecture, you have seen that we have a model that is equal to this. I will write like this. This was the exponential model. Now you can see that this one is linear model. Now what we want to do, we want to derive a non-linear model. I will write, and not just only a non-linear model, but it should hold certain condition which we will go step by step. Firstly, just we can see that if we consider the function as non-linear and if we use Taylor series expansion to expand this function of P, we will have like this: dp by dt is equal to k naught plus k1 p plus k2 p square plus and so on. Now what we will do, we will terminate our series over here and we will just consider this much of the differential equation. Now you will see that if I consider this much differential equation, I will have dp by dt is equal to k naught plus k1 p plus k2 p square, and here k naught, k1 and k2 are unknowns. Now we will use some conditions that are realistic. So condition number 1, that means that my rate of change of the population will be 0 when my population is 0. This means that there will be no change in the population if there is no population. Now if I put this condition over here, I will get k naught plus k1p plus k2 p square is equal to 0, and this implies my k naught will be equal to 0. So I get one value of the constant. And if I talk about the next condition, that is the condition that incorporates the fact that the population cannot exceed its carrying capacity, because it is natural that if environment cannot hold that much large population, the population will die if it increases over that range. So that means that dp by dt will be equal to 0 when my population will be equal to k. So if I put this, then I will get my k1p plus k2p square, because k naught is already 0. This will be equal to 0, and this gives you, so I can write over here with k, because here I have the maximum population size, so I will replace this p with capital K. Now I can take this k as common, and what I will be left with, k1 plus k2 capital K equal to 0. This one is a carrying capacity. Now if you look at this, my carrying capacity is not equal to 0, so this implies my k1 plus k2 will be equal to 0, and this implies my k2 is equal to minus of k1 divided by capital K. So this is the second thing I am getting. The first thing was k not equal to 0, and the second derivation I am getting is k2 is equal to minus of k1 upon the carrying capacity. This one is the carrying capacity, that means that the maximum number of individual that an environment can hold. Now if we put all these values in my equation, I can say as equation number 1, then what I will get? I will get dp by dt is equal to k1p plus k2p square. Now I can write it like k1p 1 minus p by k. Why I have replaced this with the expression that we got earlier over here. This is minus k1 by k. So if I replace this with minus k1 by k, and if I take it as common, then I will get this. Now I can write this as small k, this one is small k into p 1 minus p by k. This is my logistic growth model, which I have also shown you earlier. So this is a way from which we can derive a logistic growth model. Here we have just used that the population cannot grow exponentially beyond the value that an environment can hold. We have used this fact and we have derived our logistic equation. Now we will move further. You must have noticed that when p is almost, that is when p is near to 0, then you can see that the quantity in the bracket, that means this quantity, is nearly equal to 1, and the growth rate is exponential. And when you can see that the population, that is p, is around equal to k, then the bracket is approximately equal to 0 and the growth is equal to 0. If you solve the logistic equation and if you draw the graph, you will get this. So this one is a graph of exponential growth, which you can see that it is of J shape, and this is the logistic growth curve, and this one is a S-shaped curve. Here the k, that is a small k value, is taken as 1, and the carrying capacity, that is a capital K, is taken to be 1500. Now if you solve this and if you plot the graph, you will see that the population here, n means p, right, the population size. So if you solve this differential equation, you will see that a curve like this is obtained. We will see how to solve this logistic growth. So here is the analytic solution of the logistic differential equation. So we can solve this by separating the variable. So here we can take all the p variables over here, and t variables will be kept in the right hand side. And then in order to evaluate this left hand side, the integral of the left hand side, what we need to do, we need to break up into the partial fraction. So you can see that I can write this breaking up into the parts like this. Now we will put the integral over here, and then we can do simple integration, and you will finally see that you will get the solution as this. And here capital A is given by this. Here K is a carrying capacity and P naught is a initial population at which you consider as a reference point. So this is initial population. So I was talking about this only, that if you draw this graph, you will see a type of S curve, which I have already shown you. So we will talk about the graph over here. So if we analyze this curve, you will see that there are three different sections in the S-shaped curve. So initially the growth is exponential because there are very few individuals and ample resources are available for them, and as the resources becomes limited, the growth rate decreases. And finally, what is the third section? The growth rate levels off at carrying capacity of the environment. So you can see that my S curve, that is this curve, is divided into three sections. Firstly, the growth rate will be exponential, then it will decrease, and then it will level off. So you can break your curve into three parts. Now we will see a mathematical justification for this. So this is a S-shaped curve, and we have already seen that what is our differential equation. Our differential equation is dp by dt is equal to small k, if I write like this, into p 1 minus p by capital K. Now if you differentiate this with respect to t, what you will get? You will get, so I can write this as d square p by dt square k dp by dt 1 minus 2p by k. Now if I look when my d square p by dt square is equal to 0. If you see when this is 0, this is 0 when either dp by dt is equal to 0 or 1 minus 2p by k is equal to 0. So this one is 0 means that I have my 1 minus 2 p by k is equal to 0 implies my p is equal to k by 2. Now why I am talking about is that this point is an inflection point. If you remember the theory in calculus, inflection point means the concavity changes. Like if the population is moving from this point, that is k by 2, this point is my k by 2. This point, if this is k, you can see clearly that this point is population is k by 2. That means that after this point the concavity will change. From the figure you can see that here we have concave upward and here we have concave downward. So when I can write that when p is less than k by 2, this implies that d square p by dt square is greater than 0, right? That means that this is, I am talking about concave upward. And when my population is greater than k by 2, this implies my d square p by dt square is less than 0. That means that it is concave downward. So this plot is for this function, right? And if you see that if I find this, this is showing that my graph will be concave upward below this population k by 2 and it is concave downward after this population. So this is the point of inflection. This is the point of inflection. And why this is important? Because this is giving you an important analysis. Like if I write the analysis, what it is giving, that when p is less than k by 2, then dp by dt increases with time. That means what? That means that the rate of growth of population increases with time. And when my p is greater than k by 2, then rate of growth of population decreases with time. So this point is very important and it will show you the maximum point of growth will be there. This is increasing, this will be the maximum, and after this point the rate of growth of population will decrease. And here also it will be 0 and here also the rate of growth will be 0. So this was interesting observation that we can see from the logistic growth population model, and we will talk about the importance of this point in an example at the end. That is from the COVID scenario. Now we will do an example utilizing this logistic growth model. So it says that a population of the US in 1800 and 1850 is given to be 5.3 and 23.1 million people. Now they are asking to predict the population at 1900 and 1950, firstly using the exponential model of the population growth. Then we need to consider that the actual population in 1900 was 76 million of people. Now we need to correct our prediction for 1950 using the logistic model of the population growth. What is the carrying capacity of the US according to this model? So let us see how we can solve this problem. So firstly we need to start with a exponential model. So I will write down the formula for the exponential growth model, and you can see that here P naught is P0. So for P0 we will consider this one as a reference point. This one will be our P naught. So I will just write down here our P naught is 5.3 million. So according to the given information, what we have been given is that at P50, that means that I am talking about at 1850, because this was the reference point, and if you see the gap from the reference point in 1850, it's 50 years. So I can write this as 5.3 because P naught is the reference point. So this is 5.3 e to the power k into 50 because the time is 50, and from this we can find out the value of the growth rate, that is coming out to be 0. people according to the exponential growth model. So now according to the question, the population at 1900 is 76 million, right? This one is a exact value which is given, but in the exponential growth we can see that we are getting this much population, which is an error. So they are saying to rectify this with the help of the logistic model. So we will again use the data which is given at 1850 and 1900 to find the value of the small k and capital K. Small k means the growth rate and capital K means the carrying capacity. So we will utilize these two data, that is at 1850 we have 23.1 million and at 1900 we have 76 million of people. So let us use this, and then for the logistic model. So for logistic model we have Pt is equal to K divided by 1 plus A e to the power minus small k. This one is a small kt, and here A is K minus P naught divided by P naught. So at 1850, that means that 50 years from 1800, if I use now this formula, what I can write, this is unknown, 1 plus K minus P naught is what? 5.3 million, because at 1800 the population is 5.3 divided by 5.3 into e to the power minus of 50k. Again this k is unknown. This much is given to be 23.1 million. Now if I write the population at 1900, that means that is 100 year from the reference point, that is 1800. So here also I will write into e to the power minus 100k. K is the growth rate over here, and this is given to be 76 million. Now what we can do, we can solve these two equations and find out the value of this capital K and the small k. Right? We need to find out these values from these two equations, and if you see and solve, you will get capital K as 189.4 and small k as 0.031476. Now as per question, we need to find out the population at 1950. That means that 150 years away from the reference point. So I can write at 1950 the population will be 189.4. This is the value of carrying capacity divided by 1 plus, if you find that I can write k minus p naught divided by 5.3 into e to the power minus, now I will use the value which I got over here, t, and here t is what? This t will be 150. So put all the values and you will see that you are getting the value in 1950 as 144.7 million. So this is how you can use the logistic model to approximate the population in the future time. So at 1950 you can see that the population will be around 144.7 million of people, and exponential model you have found out that they were overestimating a lot because they were giving the answer as 438.8 million, and with the logistic model we are getting correct value because in actually US population as 150.7 million of people, and this is underestimating because the birth rate may have increased, but it is giving less error as compared to the exponential growth model. So now we will move further. Now we will talk about some examples of logistic model which are seen in the nature. So if you put the yeast, it is a microscopic fungus and it is used to make breads and alcoholic beverages. So it exhibits a classical S-shaped curve when it is grown in a test tube, and its growth level decreases or it levels off as the population depletes the nutrients that are necessary for its growth. So in the real world, however, there are variations to these idealized curve, and there is a next example also for the seal population, and it has been seen that seal population can exceed more than the carrying capacity for short period of time, but it again falls to the carrying capacity afterwards. And in some population it has been also observed that the population size oscillates around the carrying capacity. So here is an example. This is an example of the yeast. It is showing the growth as per as the logistic model. As you can see that here the growth is rapid, and after that the growth rate decreases and it levels off as it comes to the carrying capacity. And this is a seal population growth rate. Here you can see that this is a portion where the population exceeds the carrying capacity, but again after some time it becomes or it levels off in the carrying capacity only. So this I have taken the images from this website. Again you can see the logistic type of growth. If you grow a paramecium aurelia in a small culture, and these dots are showing you the data, and this is a logistic curve fitting into it. So you can see that this also shows you a logistic kind of growth. If you talk about the population in Daphnia, and if it is grown in the lab, it is overshooting the carrying capacity. You can see clearly over here this population overshoots the carrying capacity, and after that the death rate becomes more than the birth rate, and the population again declines back to the carrying capacity. Here you can see an example where the sparrow is in the natural habitat, but it is now oscillating about the carrying capacity rather than it is completely following the logistic model. It is now oscillating around the carrying capacity, and this sparrow is kept in the natural habitat. Others are seen in the lab or some kind of test tubes. Now we will use this logistic model for the disease epidemic. So this is a question that an influenza epidemic spread through a population rapidly at a rate that depends on two factors. So what are these two factors? The more the people who have the flu, the more rapidly it spread, and what is the second? And also the more uninfected people there are, the more rapidly it spread. So if we look into these two conditions, we can see that logistic model is a good one to study the spread of communicable diseases, and clearly the maximum value of the number of infected people will be the entire population. Now if at time is equal to 0, there are thousand of people in the community. Now suppose that at time t is equal to 0, there is only one person in the community of 1000 people who has the flu. So that means that at initially we are talking about that infected is only one person and the complete population will be 1000 people. So now if some researcher finds that the growth rate is this much, then the question is asking to estimate the number of people in this community who have flu after 10 days. So let us see how to solve this problem. So if we substitute our data into the logistic growth model, this is the solution of the logistic growth model. Here we can see that we have thousands of people, so we can set our maximum carrying capacity as 1000, and if you put these the value of k as 1000 and p naught as 1, because if we talk about how many infection are there, we are talking about that here p naught is equal to 1, because there is one person that is infected at time t is equal to 0, and we are interested in how many infected people will be after 10 days. So this p will now refer to as the infected cases, right? And so here k is 1000, a is coming out to be 99, and this small k which is given in the question is around 0.6030. So putting all the values in this formula, we can see that we will get this much of infection. It is 293.8, and you can round it off and you can say that 294 people will be infected after 10 days. So if we plot the figure and if we see that how the infection is increasing, and here we can see that on the 10th day we will have 294 cases, and after that the entire population will get the disease in about 20 days. You can see like around 20 days the entire population will catch infection. So this is how you can use the logistic model in different situations, not only for the population growth. If it is suited for the other situations or scenario, you can use the logistic model over there also. There is another interesting observation that was given by these authors in their research paper. So they have used the logistic model to fit the data for COVID-19 and SARS in 2003 in China. So what is such an interesting thing? If you remember this figure, this was an interesting point, and this point was how much? This point is k by 2, and if you put over here, you will find that your time is around this log, natural log a by k. So that means that when the half of the population from the carrying capacity is infected, after that the spread of the disease or the rate at which the disease spread will slow down, right? If you see the physical interpretation of this, below this point the rate of growth of the infection was high, and after when half of the population is infected, the rate of the spread of the disease will slow down. So they use this thing to find out the time. Like this one, this coordinate is telling you the coordinate of time. So what they have done, this is their logistic solution, logistic model solution, where k is the cap value, b is the constant that is considered to be the incubation period, this b1 is the incubation period, and a is constant, and they fitted the model and found out the value of a. So this is the key point, this ln a by b, which I have shown you why it is a key point, because after that the rate of increase is slowing down. After this point the rate of the infection spread was slowing down. So they calculated this value. This value can be easily, this b is an incubation period, and a can be found by fitting this curve with the real data, and we can find this value of A, and you can easily calculate this value, which will give you the value of time. Now if you see that the current day in the time series is less than this value, then this means that the disease will still grow exponentially. And if the current day in the time series has passed this value, that means that the spread have been controlled and it is going towards the end. So this was a very interesting observation that was made, that what does this mean by the current day? Means the day from which the infections start, or from the day from which we have the data till the current day. We will see how much days are there, and then we will compare it with this key point. And if that is less than the value of this, then it means that still the infection will grow very rapidly and there are still time so that the infection are controlled. And if this time, if the current time is greater than this value, this key value, that means that the infection is going towards the end. But there are few remarks that we need to keep in point, is that the logistic model of the population growth, while it is valid for many natural population, it is mainly the simplification of the real world population. And if you see that implicit in the model is the carrying capacity of the environment, that does not change. We do not change the carrying capacity, and which is not the case. You can see that the carrying capacity changes annually for many of the species. For the winter they have lower carrying capacity, for the summers they become high. And also for the natural events like earthquake, volcanoes, fire can also alter the environment and hence the carrying capacity. Additionally, populations do not exist in isolation. They share the environment with the other species also. The other species also compete for the same resources. And these factors are also very important to understand how the specific populations will grow or will decline. So it is very important for the wildlife biologist to understand all the factors and help the population to manage themselves and to prevent extinction and overpopulation. So in today's lecture we discussed about the logistic population growth. In the coming lecture I will show you few prey predator models, that how the two population compete with each other and how we can model those type of scenario in my next lecture. So I will end this lecture over here. Thank you.